Hello dear students, this is Tamás Jávor. Welcome back to Rubber Duck Physics. Today we are going to explore a new concept, accelerating rotational motion, which we can describe by angular acceleration, and the equations we can use to calculate values of kinematic quantities in it. Just like linear acceleration describes how fast something speeds up or slows down in a straight line, angular acceleration tells us how fast something's angular velocity changes as it rotates. Let's start by mathematically defining angular acceleration. It's the change in angular velocity over time, and we use the symbol alpha for it. The formula looks like this. Alpha equals delta omega divided by delta t, or the change in angular velocity over time. In my opinion, angular acceleration is even more abstract than linear acceleration. If you want to grasp its nature in a short sentence, we are talking about the rate of change of angular velocity, where, I hope you haven't forgotten yet, angular velocity is the rate of change of the angular position of something. Got it? You can pause the video and repeat or note it down, highlighting the key terms. This reasoning directly yields the unit of angular acceleration to us. Angular acceleration is the change in angular velocity divided by the change in time. The unit is 1 per second, we know 1 here is for radians, divided by second. That is 1 per second squared. Now let's talk about positive and negative angular acceleration. If the object's angular velocity is increasing in the counterclockwise direction, then the angular acceleration is positive. If it's, however, slowing down clockwise, that can also result in a positive angular acceleration. And the opposite way, when the object's angular velocity is increasing in the clockwise direction, angular acceleration is negative. And if it's slowing down while rotating counterclockwise, angular acceleration is also negative. Here is where students often get confused. A negative angular acceleration doesn't always mean the object is slowing down, losing angular speed. It depends on which direction the object is rotating. For example, if the object starts with an angular velocity of negative 2 radians per second and speeds up to negative 5 radians per second, the change in angular velocity is actually negative 3 radians per second, meaning it's actually speeding up in the clockwise direction. Now let's look at the 4 kinematic equations for uniform angular acceleration. They are just like the equations we use for linear motion, sometimes also called Souvet equations, but with angular quantities. First, we have omega final equals omega initial plus alpha times t, which tells us the final angular velocity after a certain time. Next, we have theta equals omega initial times t plus 1/2 alpha t squared, which helps us calculate angular displacement. Then we have omega final squared equals omega initial squared plus 2 alpha delta theta, which relates the final angular velocity to the angular displacement. And finally, we have theta equals 1/2 omega initial plus omega final times t, which gives us the angular displacement based on the average angular velocity, half of their sum. Let's try applying one of these equations with a spinning disk. Imagine a potter's wheel that starts from rest and begins to accelerate. We can use the kinematic equations to figure out how fast it's spinning after a certain amount of time, or how much it has rotated. Now let's compare angular acceleration to linear acceleration. In linear motion, acceleration tells us how fast an object is spinning up in a straight line. In rotational motion, angular acceleration describes how fast something is speeding up or slowing down as it rotates. A great everyday example of angular acceleration is a ceiling fan. When you turn on a ceiling fan, it starts from rest and gradually speeds up. That's angular acceleration. The blades are accelerating until they reach their final speed. Both types of motion follow the same basic principles. For example, just like a car speeding up on a straight road, a spinning object can speed up as it rotates. And just like the car can have negative acceleration while traveling in the positive direction, that means braking, a wheel or the fan can have clockwise, that is negative, acceleration while rotating counterclockwise, that is in the positive direction, if its rotation is slowing down. Till the next video, let's think about something fun. Imagine being on a merry-go-round. If you sit near the center and ask your friend to spin you, it's easy for your friend. But what happens when you move out towards the edge? It gets harder to turn. Why does that happen? I guess you didn't gain much weight while sitting on the merry-go-round. This is due to a concept called moment of inertia. Just like on a merry-go-round, the distribution of mass affects how easily something can rotate. In the next video, we'll explore how moment of inertia plays a key role in rotational motion and affects how objects speed up or slow down rotationally. Today, we have learned how to describe angular acceleration and how it changes an object's angular velocity. Next time, we'll dive deeper into moment of inertia and discover why moving farther from the center of a rotating object makes it harder to spin. Need a little extra support with your physics coursework? I am here to help. I provide online tutoring for IBDP Physics, A-Level Physics and Maths, and AP Physics. You can find my email in the channel description on Rubber Duck Physics. Just remember to check it from a web browser. Feel free to contact me for more details or to schedule a session. Thank you for watching the video. See you next time.